Hey Baker fam, it's your science teacher, Miss Swanson. I'm here in case my lesson doesn't go according to plan, and I actually have to record and give you guys a lesson on S and P waves. Don't say it the other way, it sounds funny, which is why we use S and P waves in explanation. So, when an earthquake happens, right, it starts shaking, and that shaking is the transfer of energy from the original location, which is called the epicenter, the original location, and reverberates outward. And there are two main waves that an earthquake releases, and waves are a transfer of energy, right? So there are two main waves that transfer energy from an earthquake. They are called S waves and P waves. So here I have two different images, or I have two different waves here. This top one here is S waves, and this bottom one here is P waves. And I am going to link in my YouTube this video, that way he gets credit for it, because this is a really nice video of S and P waves. Normally we would be in the classroom moving slinkies around to see the same thing, but we don't have a classroom right now. But hold on, we have a few more weeks and we'll have a classroom. So we've got S waves, and they go like this, right? And we got P waves, and they go like this, right? One of the simpler ways that we call S and P waves is we call S waves side-to-side waves, and we also call P waves push-pull waves, because it looks like the molecules are moving side-to-side on the S waves and pushing forward and back on the P waves. Some things about S and P waves. P waves are your primary wave. S waves are called secondary waves as well, which is also why we say P waves, primary, P, make it easy, and S waves, which are the secondary waves, and shorten it to S waves. P waves are also known by a few other names. They are also compression waves, and they are also called longitudinal waves. And it has to do with the particle motion. So the further you get into physics, the more complex these two waves get. Right now it's just an introduction to what waves are and how waves transfer energy from one thing to another. But as you get deeper in, they have more in-depth explanations for you. And so P waves are also known as primary waves, push-pull waves, compression waves, and longitudinal waves. Let's exit out of that so you don't see the email notification. S waves are known as secondary waves. They are also known as side-to-side waves, transverse waves, and surface waves, because it kind of looks like it's on the surface of the water, right? And both these waves travel the same areas of the earth, right? So I'm going to bring up my handy dandy paint for you and kind of show you on this drawing. So you have a normal planet, right? You have Earth, right? There's Earth. There's America. There's South America. There's Africa, India, Russia, Europe. Okay. Okay, general idea, right? So the Earth starts shaking. Let's say the Earth starts shaking right here. The surface waves will travel all the way along the, surface, the outside of the planet. Because if you didn't know, if you don't remember, our planet actually has a solid core and molten lava. Well, magma. Technical term. Don't call it lava. Lava means on the outside. Molten magma. And on the outside there, it is... so transverse waves can travel through water. But this surface waves, the secondary waves, do not travel through the center of the Earth. So what's going to happen is you have waves that go this way, right? Out this way. But then you have transverse waves that go this way, right? They travel as fast as they possibly can in that area, in that direction. So that comes to my next point, right? Out of S and P waves, that's an R. S and P waves, which one do you think is faster? And while I set up this next section, hopefully you kind of understand, you've kind of already guessed whether or not you think S or P waves are the faster wave. All right, so here we go. Why does it matter? What? Brushes. Marker. Why does it matter that the waves are slower and faster? We're going to do this chart here as best as we possibly can. That looks terrible, but you'll get the idea. Why does it matter if it is a different speed? Well, the trick is we kind of have to want to know where the earthquake happens. We want to know where the earthquake happens and where we could potentially experience an earthquake again. Time and time again, we know that Earth's processes happen for a reason and over in particular times. For instance, you're not going to see a volcano erupt, in Utah. You wouldn't expect that because there aren't any volcanoes there. So we know volcanoes erupt in the same areas over and over again. So with that in mind, we want to try and pinpoint the location. So if 0 here is where the epicenter is. Okay, we have 0 here. Where's the epicenter? Oh, and you can't even see because of my camera here. Let's fix that. We're going to make that nice and small. There you go. There we go. There we go. We'll move that up here. Voila. Yeah. Okay. So I'm up here in the corner now. Back over here. Oh, I didn't mean to do that. Okay. So we have the epicenter here, where 0 is the epicenter. And we have the two waves right here. And this is when, if we look back to 7th grade, right? You guys had to do motion and forces in motion. That's what the unit was called in 7th grade. So what is distance and time, right? Distance, why does that look like a P? Times time, okay? What's that called? You guys remember? Speed, hopefully. Okay, so we have this idea here that we have the epicenter at 0, 0, and distance times time, right, is speed. And I just asked you, before I set this up, what wave do you think is faster? And hopefully you're right. So if we go, is this one faster or is this one faster? This one is time in minutes, so this wave has to be faster. Come on. P wave. S wave. Okay. Sorry for my writing. It happens. That's what happens when you're writing on electronics right now. My electronics are a little old, but so we have this here. We have S wave, we have P wave. And we can actually determine that the distance between the two lines here can determine a distance in miles, where I'm like hundreds of miles away from the original location, right? So, and if we look here, right, we go down, whoop. So we've got 0 here. And if it's no time in between the S and the P waves, you're hit very hard but you know that's where the epicenter was. That's if you're lucky enough that there is no difference between the S and P wave, you're on the epicenter, that's where it happened. However, with most earthquakes, there is not usually a seismogram in the epicenter just randomly chilling there. We have a lot of ones, right? We have one in Alaska, we have one in Bellingham, we have one in, we have some in California, we have some in Hawaii. So we do have seismograms everywhere to be able to take these seismographs. We have seismographs to take the seismograms, but we have seismographs in specific locations, but it's very rare for them to have and be in an epicenter. So we want to try and find this epicenter location with the P and the S waves. As you remember, right, the S and the P waves travel a certain location. So if you are a seismograph and you're in this location, you're going to experience the P wave first, and then you're going to get hit with the S wave. And the time in between those two will actually create this chart here. And you can actually pinpoint how far away the earthquake was depending on how far away the S and the P waves are. Right? So that's why it's important to understand the speed of an earthquake or of these P and S waves. I said it the wrong way, but I said it slow. S and P waves. So there is some distance between the two, like right here. What? If I were to measure this distance from this distance, it would be different from this distance and this distance and this distance and this distance. So it's the time in between the hitting of the P wave and the hitting of the S wave that actually causes you to understand how far away the earthquake was. Was it 1,100 miles away, which is 1,100 miles away? Was it 500 miles away? Was it only 100 miles away? So you can actually tell this based off of seismograms. So, Ms. Swinton, is that all I need to do? Well, not quite. Because the reason why I say that is, so let's say there's an earthquake here, right? So you guys know that we live right here. And there's, boogers. Gotta get that marker going. We live right here. And I don't like that. I want to do bright orange, yeah. Orange, no, orange won't show up in this colors. So we live right here in this area. If we identify that there's an earthquake 100 miles away, that's all we get. That's the only information. It can be here, it could be here, it could be here, 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 here. Okay, right? It could be all around there. The only problem with that being is, well, we want to know where the earthquake happened. If the earthquake happens right here, it's not going to help us, or right here. Having this ring here doesn't help us in identifying where we should use safety measures, right? The unit before this, we actually spent a lot of time and effort building our earthquake-safe houses. That's money, right? That's money that doesn't need to happen if you live right here and the earthquake hits right here. It's not necessary for us to have to build earthquake-safe houses here. They need to invest their money in building a different kind of house that would, realistically help them against tornadoes, probably, right? You remember in 6th grade, tornadoes, boogers. What does undo? Undo. I'm touching the thing with a razor. All right. So let's do pink, actually. Yeah. So we're right here, and we've got an earthquake that's gonna hits us, right? And we've identified that through the S and the P waves, we've identified that the earthquake is somewhere along this ring, okay? There is a seismogram here, and there is, and it identifies that the same earthquake. So the trick is you have to be measuring the same earthquake. The same earthquake is this far away. Okay, so this particular Hawaii seismograph has identified that the earthquake is here. This identifies 2 locations now that could potentially be the location of the earthquake, which means we need a 3rd location to tell us where the earthquake was. So go back to our pink. So there was a seismogram in California, and California is telling us it is that far. My circles went so well until just there, right? And so we can actually identify that the official location of the earthquake was right there. Because we have 3 locations, this process is called triangulation, right? Identifying the location of this earthquake, we've triangulated the earthquake using 3, right? Pretend it's a triangle, 3 locations to do this. So you cannot triangulate an earthquake using only 2 cities, right? Because you get a huge discrepancy, right? Was it in Oregon or was it in Canada? Totally erases Washington, right? So you have that location centered down. So you know if you are in a house, obviously Hawaii felt it, but Hawaii was not impacted by it. Neither was California. They could feel it. Their seismograph took data on it. They could tell the S and the P waves, but they didn't get affected by it. So if you were living right here, let's say you're in Vancouver, you might want to, build earthquake-safe houses. Your big buildings should be on something that can withstand a pretty substantial earthquake. Because where an earthquake happened once, an earthquake can happen again and again and again, which makes it a little difficult when we're trying to find earthquakes. So, put it all together, we know that earthquakes make S and P waves. The S waves travel slower than the P waves, which allows us to identify how far away the S and the P wave happened, right? How far away the epicenter of the earthquake was. And we can triangulate with 3 seismograms in 3 different locations where that seismogram happened, or where that epicenter happened. And that is basically the boring version of the game that I was having you play, but couldn't play for you because the computers weren't working. So you get to watch a video of me teaching you the ideas and thoughts. Now it is your turn to identify the location of the earthquake. Oh, I guess I should probably add in one more thing. How does a seismogram, let's open up a new one. How does a seismogram actually identify where the P and the S wave is? Well, we know the P wave comes first. So in a seismogram, you're going to go, right? It's going to be like, oh, it's a happy day. Oh no, an earthquake, right? Oh no, an earthquake, right? And the first location is the P wave. And the second location is the S wave. So your primary wave here, your secondary wave here, and that's how earthquakes go. So this is actually a time, right? 1 minute, 2 minute, 3 minute, 4 minute, 5 minute, 6 minute, 7 minute. So it's counting down like that. And once that happens, you can actually tell that it was, 3 minutes apart from the P and the S wave. And then you come back over to here and you look at where the P and the S wave are 3 minutes apart. So if each one of these squares are 3 minutes, I'm going to go through and I'm going to go and look through where 2, 3. I'm going to look at where the P and the S wave are 3 minutes apart. And this is kind of why it's important to do math, right? To take your algebra seriously. Because if you don't take your algebra seriously, you won't understand how to do this map. When you get into your own profession and they ask you to analyze, it doesn't matter what it is. Even if you do manual labor, they're still going to ask some sort of information from you with mathematical, algebraic thinking. Which is why they're teaching you graphs in algebra right now. So we've got this location right here. So we know it was 300 miles away. Which, to be fair, the seismogram that I created, not that I created it to look like that, but it looks like, realistically, this earthquake from Washington was about 300 miles away. If you guys know distances of areas in the earth, which... not very many people do. I only do because I teach this every year for 10 years straight. So we've got 3 there, and we need seismograms, right? The seismograph takes this data. We need seismograms from 3. Right there. There's the first P wave. And there's the first S wave. Still same times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Forgot all. Right? And so here's the first wave in Hawaii, and there's the second wave. This is the Hawaii reading, and this is the Washington reading. And then the California reading will be even smaller, but still a little bigger, right? So your first wave, your secondary wave, it'll be a little further away, but then you take it over to the chart. Nope, not teams. You take it over to the chart, and you identify where, 6 minutes apart were. And you can identify that with a seismogram. So, in short, all together, we'll do it again. In conclusion, hopefully you either listen to this at full speed or you were able to get the game working. If not, surprise, you're here listening. So you've got S and P waves. Those are the 2 main types of earthquake waves. P waves can travel faster. S waves travel slower. Then you take it over to the, chart here based off your seismograms, and you identify how far away they are. And then you can triangulate based on how far that earthquake was away from that location. You can triangulate the earthquake and its location. So you can tell people in Vancouver to make earthquake-safe houses, and people in, Texas to not worry about earthquake-safe houses. Maybe they should make, maybe if that's the correct location, maybe they should make, drought or flood-safe houses. Texas has not had a good year this year. Sorry, Texas. So, that being said, these locations, pinpoint, identify, save money, divvy the resources to where they're needed, because they aren't needed in locations that don't have earthquakes. They don't need ball bearings underneath the buildings to make earthquake safe buildings in any other locations if they aren't going to have earthquakes. I hope this was helpful. If you have any questions, just ask in class, and have a great day. Bye!